Hello everyone. In this video we are going to learn about the polynomial remainder theorem. Let's say we have a function uh, and that needs to be divided by a certain linear expression. Let's say fx is equal to x square plus 4x plus 7, and we want to divide it by x plus 1, and we want to see what is the remainder when we divide this polynomial by x plus 1. One way we could do is just use the long division. So we write 2x square plus 4x plus 7, and then simply divide it using a long division method by x plus 1. So all we do is write x here, multiply x with x plus 1, we get x square plus x, and subtract this one, so we get 3x over here and plus 7. Now I can multiply this x plus 1 with 3 to get 3x plus 1, 3x plus 3, and when I subtract it I get remainder 4. So the 4 is the remainder when you divide this expression by x plus 1. Now there is another way. Let's try to find this remainder. The way is you substitute x plus 1 equal to 0. This implies x equal to minus 1. And now what I do is I substitute x equal to minus 1 in this equation to get f of minus 1. So f of minus 1 is going to be minus 1 whole square plus 4 into minus 1 plus 7, and this is equal to 1 minus 4 plus 7, or 4. If you notice, this remainder 4 is the same as the value that we got from here. And why does it work? To understand it, let's go back to this equation fx equal to x squared plus 4x plus 7, and look at this our long division method. So when I divided fx by x plus 1, I got x plus 3 and 4 as remainder. So I can write it by 4 divided by x plus 1. And why I can write it like this? Just imagine you are dividing a number 47 by 5. How do you write it? You write it at 9 plus the remainder 3 divided by 5. So I can also write this in this format. Now I multiply this whole equation by x plus 1. So what I get? Fx multiplied by x plus 1 divided by x plus 1 equal to x plus 3 plus into x plus 1 plus 4 into x plus 1 divided by x plus 1. And if you simplify this thing, this x plus 1 cancels here, so we simply get fx equal to x plus 3 into x plus 1 and plus 4, and this 4 is the remainder. Now all you do is, in place of x, write minus 1. You substitute x plus 1 equal to 0 in this equation. if x plus 1 is equal to 0, then x equal to minus 1. So I can write f of minus 1. This term becomes 0 because x plus 1 is 0 and the remainder is 4. So what it is saying is that f minus 1 is 4, and this is the result that we got here. I would urge you to go through this exercise, write it down one more time on a paper and a pencil, and you will understand it better. So let me formally express this result in a formal way. This is what the polynomial remainder theorem can be expressed in a formal way. If a polynomial fx is divided by x minus a, then the remainder of the division is fa. We started our example with with a value of a as minus 1, but that's the same thing. So for example, if fx, let's say, if fx let's say is equal to 3x square plus 4x plus 2, and you divide this polynomial by, let's say, x minus 3, then the remainder will be given by f of 3 is equal to 3 into 3 square plus 4 into 3 plus 2, or you can do the calculation, 27 plus 2, 29 plus 12, 41. Let's take a look at one more simple example, and you need to practice more problems, starting with simpler problems to more complicated problems. That's the only way you will be able to understand it better. So we have a polynomial, and I will keep a link below in this description. So check it out and go through some problems. So if px equal to is divided by x minus 1, the remainder is 4, and what is the value of k? Very simple problem. So what we do is, when I divide it by x minus 1, then I substitute x minus equal to 0 or x equal to 1, and then the p1 will give us the remainder 4. And what is p1? We substitute instead of x 1, so 3 into 1 squared minus 5 into 1 plus k is equal to 0. Okay, then 3 minus 5 is minus 2 plus k equal to 0, or k is equal to 2. This is going to be the right answer. So I hope you all enjoyed it. Make sure you do as many problems as possible to practice this remainder theorem. It's a very useful theorem, very simple but very powerful.